All right, today we're going to pull back the curtain on a really powerful mathematical idea that, believe it or not, shapes a huge part of our digital world. We're going to break down and demystify something called the Markov chain.
So let's start with a crazy question. With billions and billions of web pages out there, how does a company like Google decide which ones are actually important? I mean, think about it. Back in the late 90s, this was the problem to solve. And the answer, as it turns out, wasn't just about, counting keywords. It was way deeper. It was about understanding the very fabric of the web.
And their solution? It was this brilliant algorithm called PageRank. And I mean, it wasn't just a feature. It was the absolute heart of Google when it first started. For a long time, you could actually see a page's rank right there in your browser's toolbar. Now sure, today it's just one piece of a much bigger puzzle, one of hundreds of signals they use. But the core idea behind it, that's just as important today as it was back then.
Okay, but here's the kicker. The real secret sauce behind this revolutionary, multi-billion-dollar algorithm, it wasn't some flashy, brand-new piece of tech. Nope, it was actually a mathematical idea that came from a Russian mathematician named Andrei Markov over a century ago. How crazy is that?
All right, so let's dig into the core idea here. We're talking about the memoryless machine and the one fundamental principle that makes this entire thing tick.
So, the entire concept really boils down to something called the Markov property. And what it says is, it's pretty simple actually. To predict what's going to happen next, you only need to know where you are right now. That's it. The whole long journey you took to get here, totally irrelevant. And that's exactly why people call it memoryless.
Now, this is the exact analogy that Google's founders latched onto. Just picture a random surfer on the web. They're not thinking, they're just clicking links, mindlessly. Where they go next depends only on the links available on the page they're on right now. They have zero memory of the 10 or 100 pages they saw before this one. Their next move is decided entirely in the moment.
Okay, so let's take that surfer idea and get a little more formal. We're going to break it down into the actual building blocks of what a Markov chain is. So let's make this super clear. The state space, that's just the entire internet, all the possible pages our surfer could ever visit. The transition probability, that's simply the chance they'll click from, say, page A to page B. Now the transition matrix, that's the big one. Think of it like the ultimate rulebook or a giant map of all those probabilities. And finally, the initial distribution is just, where does our surfer start? Which web page do they begin on?
And to see how this works outside of the internet, check out this simple weather model. Here, the states aren't web pages, right? They're air pressure, high, medium, or low. And the arrows? Those are the transition probabilities. So for example, you can see the arrow pointing from high to medium pressure has a 0.4 on it. That just means there's a 40% chance of that happening. It's a super clean, visual way to see the system's rules.
Okay, so that visual map we just looked at, you can take all that information, the states, the probabilities, and put it into a grid of numbers. And that grid is called the transition matrix. But you got to understand, this isn't just a boring table. It's literally the engine of the whole Markov chain. It's got all the rules baked right into it.
And once you have that engine, the transition matrix, this is where things get really, really cool. You can actually start to predict what the system is going to do in the long run.
So let's jump back to our random surfer. What if we just let him go? Forever. Clicking links for an infinitely long time. Billions of clicks. Could we actually predict which pages they'd end up spending the most time on? You'd think it would be pure chaos, right? But the answer, incredibly, is yes, we can.
The magic behind this is something called the stationary distribution. Okay, what is that? It's basically a set of probabilities for each page or each state that eventually just settles. It becomes stable and stops changing over time. It's like the system finds its natural balance. And the wild part is, it doesn't matter where our surfer starts their journey. Eventually, the amount of time they spend on each page will perfectly match this final stable distribution.
And this isn't just some kind of philosophical idea or a lucky guess. There's a straightforward mathematical process to find this stable state. You take your transition matrix, you set up this core equation, pi times p equals pi, and you solve for that probability vector, pi. The only rule is that all the parts have to add up to 1, or, 100%.
And here it is. This is the big aha moment. This quote just brings it all together. A Google PageRank is just a finite Markov chain of pages that eventually converges to a steady-state vector. Steady-state vector? That's just another fancy name for the stationary distribution we were just talking about. So let me say that again, but simpler. A page's PageRank value is literally just the long-term probability that our random surfer will end up on that page. That's it. So the more important pages, the ones with lots of good links pointing to them, they naturally have a higher probability of being visited. And boom, that's their rank. It's just that elegant.
But look, this idea is so much bigger than just ranking web pages. It's not a one-trick pony. So let's check out a few other, kind of surprising places where these memoryless machines are doing some heavy lifting.
I mean, the applications are just all over the place. People in finance use them to model the odds of the stock market switching from, say, a bull to a bear market. The predictive text on your phone. That's right, it's using a Markov chain to guess the next word you're going to type based on the word you just wrote. And we see the same fundamental ideas in everything from weather forecasting to economics to biology.
Take genetics, for instance. A sequence of DNA is like a perfect little Markov chain. The states are just the 4 chemical bases, A, C, G, and T. And by figuring out the probabilities of transitioning from one base to the next, scientists can actually build models that find the important parts of a gene, like the exons that code for proteins and the introns that don't.
Okay, and this brings us to a really important next step, the hidden Markov model, or HMM for short. So with a normal Markov chain, everything's out in the open. We know exactly what state we're in. We know what web page the surfer is on. But with an HMM, the real state is hidden. Think about it like this. We can see if it's rainy or sunny outside, right? That's the observation. But the underlying state that's causing it, the high or low air pressure system, that's hidden from us. These HMMs are absolutely critical for really complex stuff, like speech recognition, where the sound is the observation, but the hidden state is the actual word you meant to say.
All right, so after all that, what's the one big idea you should walk away with? Let's boil it all down.
It really all comes back to that one kind of weird but super powerful idea, being memoryless. By completely ignoring the past and focusing only on where you are right now and the chances of where you'll go next, this surprisingly simple model lets us predict the long-term stable behavior of systems that seem impossibly complex. We're talking about everything from the whole internet to a single strand of your DNA.
And that just leaves us with one final question for you. Now that you have this new way of looking at things, where else in your world can you see it at play? I mean, think about your own daily habits, or the way traffic flows in your city, or even market trends. How many of those complex systems could actually be understood, not by digging through their complicated history, but by seeing them as a simple chain of memoryless transitions?